Recording in progress.
Good morning, this is your Stat Sensei, Mr. Spensei, and we're going to talk about sampling error and do some multiple choice, and this is going to be a slightly longer video than the previous. So, recall that we define statistics as a study of how to collect, organize, display, describe, and analyze the data from a sample in order to make generalizations about the population parameter of interest. Also, remember the parameter is a numerical measurement of a population. It could be something like the mean, the mode, the variance, the range, etc. Um, and that is if it is the true population measure, it is the population parameter. From the sample or subset of the population, we find the estimates. That estimate is known as a sample statistic, and we just refer to it as a statistic. So a statistic is a measurement of the sample and estimates the population parameter. All right. So when we're talking about a sample, we talk about the sample mean or the sample median as opposed to the true mean, which would be the population parameter, or the true median. Sample mean is a sample statistic, it's the sample average. The true mean is the population mean or population average. So, for instance, if I wanted to know the true number of hours that Somerset students sleep on average per week, I could find an estimate by taking a random sample of 50 Somerset students. If I took a good sample, one that looks like the population or represents the population, my findings will be pretty close to the actual number of hours that slept per night. If I put 50 names in a hat and draw, I should get a pretty good estimate. However, it's likely to differ a little bit because I didn't conduct a census. That difference between my sample value, as 50 I drove, and the actual true population is the sampling error or sample variation. Error or sampling variation is the variation due to random chance, and we can describe it with probability, and it can be minimized by increasing the sample size. If I go from 50 to 100, I'm more accurate. If I go 100 to 200, I'm more accurate. If I take 1153, which is the size of the school, I'm perfectly accurate. I hit everybody. But since we're going to do a sample as opposed to a census, we're going to have a little bit of error in. All right. So sampling error is the difference between our sample statistic and the true population mean, and it can be minimized by increasing the size of the sample. Can't be eliminated, but it can be minimized. All right. Um, because there are so many variables or factors within a population, it's nearly impossible to design studies that account for every variable without conducting a census, which in itself has its own difficulties of not being impossible. Because we cannot account for all those variables, we have to involve chance in the selection of our sample to equalize the effects of variables that cannot be accounted for. So we involve chance to equalize variables that we can't account for. Even with a well-designed study or experiment, the sample statistic is only an estimate of the population parameter. Please note the word estimate. The difference between the true population parameter and the sample statistic is sampling error. Recall that when we run our simulations, there were multiple approaches that were all considered acceptable, but led to different responses. However, as we increase the sample size, the amount of variation in our responses decreased. Even though we chose different numbers to represent, as we increase our sample size, we get closer. It makes sense that if we increase our sample size, that our result would be closer to the true population parameter. We can say that as we increase our sample size, that the difference between the population parameter and the sample statistic will be less, and that leads us to say that the amount of variation diminishes as our sample size increases. Obviously, our population may be more varied as the sample size increases, but on average, the sample statistic will vary less. Caution: do not confuse sampling error with bias. Sampling error is a term used to describe properly collected data that didn't perfectly match the population. The estimate wasn't exactly the same as the population parameter. All right. In other words, given a proper method of data collection was employed, I would expect my sample to vary a little from the population. In other words, try this. If I put 1,153 names into a hat and you drew 50 and someone else drew 50, would y'all draw the same 50 names? And the answer is probably not, right? Would you expect the average to be slightly different? Probably so. So that's the case with sampling error. Sampling error is impossible to eliminate, excuse me, without doing a census. Sampling error is impossible to eliminate, but we can minimize it by increasing the sample size. So increasing sample size will help to minimize it, but we can't eliminate it unless we do a census, which we've already said is all but impossible for most situations. Unlike sampling error, bias is a problem in the design or method of collecting data. Let's highlight that. Super important. Increasing sample size will not fix bad data, will not fix biased data. Biased data cannot be fixed and must be discarded. To eliminate bias in our data collection, we must be careful in the design and the execution of our study. So must be careful in our design and in the way we carry it out. Please remember, bias is the result of poor methodology and will systematically over or underrepresent a part of the population and cannot be increased by fixing sample size. Cannot be decreased or fixed by increasing sample size. So let's take a look at some sampling error problems. Graph X and graph Y represent two samples from the same population. All right. And this population has a mean of 15. Well, in this one in graph X, all of them equal 15. And here I have half equal 20 and half equal 10 and half equal 20. Well, that means the average is 15. So based only on the graphs and the fact that the population has a mean of 15, so this is our mean right here, and I'm putting mu for mean. Are either of these biased samples and biased estimators? And the fact is, no, neither are biased estimators for the mean because both have the sample means equal to the population. This one is very clearly equal to 15. And if I take this one and I added up all the values, it would also equal 15. So 10 plus 10 and 20, 15, 10 and 20, 15. So this averages out as well. So neither are biased estimators for the population mean. Which sample has the largest sampling variation? Well, this one has no variation. Everything's exactly the same, no variation. So that means Y, having farther away, has more variation. So sample Y has larger sampling variation with data values at 10 and 20, while sample X has no variation at all. All right, B, the 5 dot plots below represent samples taken from the same population that has a mean of 15. Okay, so there they are. Which sample has the smallest sampling variation? Well, to have the smallest, I want to be as close to the center as possible. Well, my center is 15, and the one with the most in the center is C. So C has the smallest sampling variation because it has the most data in the center and the least out at the extremes at 10 and 20. Number two, which sample has the largest sampling variation? The largest sampling variation is going to have the one with the most on the outsides and the least in the middle. Well, this has the smallest in the middle and the most outside. So E has the largest sampling variation because it has the least amount of data in the center and the most amount of data at the extremes. Five estimators for a parameter are being evaluated. The true value of the parameter is 0. All right. So we know that it should be 0 and we should be centered on 0. All right. Simulations of 100 random samples, each of size n, are drawn from the population. For each simulated sample, the 5 estimates are computed. The histograms display the simulated sampling distributions for the 5 estimators. So there they are. We got 5 estimators. All right. Which sampling distributions have unbiased estimators? Well, it's supposed to be centered on 0. so E is not, so it's biased. Supposed to be centered on 0. D is not, so it's biased. C is biased because it's not centered on it. So A is centered on it and B is centered on it. So A and B are unbiased estimators because their sample statistics appear to be centered on the true population parameter of 0. All right, so A and B would be the unbiased, and C, D, and E are biased. Which sampling distribution is the best estimator for this parameter? Well, to be the best estimator, they need to be unbiased. So A and B are both unbiased. So one of them, but the one that has the least amount of variation is B. So B would be my preference. C, D, and E are biased and should not be used. A and B are unbiased, but B is the better estimator because it has less variation than A. All right. So typically speaking, these are both of these are unbiased, but this has less variation, so it's better. All right. Remember, increasing sample size. That increasing sample size decreases but not eliminates sampling error, does not fix, and does not decrease bias. So increasing sample size minimizes but does not eliminate error. It does not fix and does not decrease bias. So researchers working for a certain airline are investigating the weight of carry-on bags. The researchers will use the mean weight of a random sample of 800 carry-on bags to estimate the mean weight of all carry-on bags for the airline. Which of the following best describes the effect on bias and variance of the estimator if they increase the sample size? So increasing sample size, does that do anything to bias? No. So it says bias will decrease. False. Bias will increase. No. All right. Bias will decrease down here. No. So it's got to be one of these two. Bias will remain the same. But if we increase sample size, what happens to variation? Decreases, but not eliminate it. So it will decrease it because we went from 800 to 1300. So as we increase our sample size, the sample size goes up, our variation will decrease. And our answer choice to that will be C. All right, I hope that helps. Understanding how sampling error diminishes but not go away if you increase sample size. And I hope you have the idea that you can't fix bias and increasing sample size has no impact on bias. It's still biased. Appreciate you watching. Look forward to seeing you on the next one. Thank you.